if you have a black hole, classically, nothing can escape. So the area of a black hole can only increase. So stuff can fall in, nothing can come out. But then if you add quantum field theory to this, and if you look at what happens to small quantum fluctuations around black holes, there's a mechanism which allows the black hole to evaporate away its mass. We can find those behaviors in analog systems, in real life systems. These analogs are just analogs, and they will not prove if real black holes evaporate, but they do give us an idea of how difficult it is to actually, in a hands-on experiment where I can turn some knobs and try my best to make this effect big, how difficult is it really to test it? And then also to see how robust it is. So if you sit in your bathtub and you pull the plug, and let's assume it's a big bathtub, not a very small one. So you slowly see the water decreasing, and you have a nice vortex sitting in your bathtub. And what you have is actually a small rotating black hole that has two very strange features, which are that you can take the center of the vortex and you can look at a distance, the radius around it, and there are two special radii. One is where the radial component of the velocity field is bigger than is faster than the little ripples on the surface can propagate. So if a little fluctuation is inside this region, it will be drained, it will leave the bathtub. Then there is a region just outside that, between this region of no return for these ripples, and outside there's another region, which is called the ergo region, where the total velocity, so the angular and radial velocity, is faster than the propagation speed. So if a ripple comes, it cannot counter-propagate to the total velocity, so it has to get dragged along with the rotation of the flow. And so in this sense, you have all the important ingredients of rotating black holes. You have this region where you have this frame dragging, and then you have this region of no return. So it's a rotating black hole in your bathtub. So we have a big setup. It's a rectangular tank. It's 3 meters long, 1.5 meters wide, and about 0.5 meter high. And what we're doing, we feed in the water in a particular way so the flow gets angular momentum. So we push the flow in a certain way when we feed it in from two sides so that you have angular momentum. And so we form this gigantic bathtub vortex. And then what we do is we look at the ripples on the surface. They can actually interact with this. They propagate towards the vortex, the bathtub vortex. They scatter with it, and they can extract a tiny bit of angular momentum from the bathtub vortex. And that's the same mechanism around rotating black holes, where by scattering with scalar fields around it, it can actually radiate off its angular momentum. You can look for Hawking radiation, and that's actually quite an exciting time to discuss about Hawking radiation with analog gravity systems, because we have a lot of results already, and we have some very new and exciting results. And the media people look at, again, are water flows, open channel flows, so one-dimensional systems. You can probe it with particular small perturbations which you generate in your setup, and you see what's happening to them. And what you see is you send in a wave into this analog white hole, black hole, and you see that this wave gets converted to two waves. And these are these Hawking pairs. So it's a pair creation process. And one of them carries this negative energy, which in principle can extract energy from a black hole, an astrophysical black hole. And the other one has this positive energy. So you get this pair of particles with this different energy behavior associated to them. So I just like this, taking something really complicated and making it so simple. Because if you can show it works, you've learned a lot about the universality and robustness of physics. And that, in my opinion, gives you a much deeper, that's when understanding begins.